Hi, and welcome to the special archive edition of the Computer Chronicles. I'm Stuart Chaffee. Several years ago, we did a special two-part series entitled Computers and the Pentagon, taking a look at the use of technology by the military. At that time, of course, the potential enemy was Russia and the Soviet Union. Times have changed now as we face a more amorphous enemy in what is being called the first war of the 21st century. Now, much of the technology being used today was developed in the mid to late 1980s, so what you are going to see is very relevant to what is going on right now in 2001. We're going to begin by taking you on board the USS Valley Forge off the coast of California to show you Aegis, an automated battle system being used by the Navy. Then we'll go to Rome Air Force Base in New York to show you how pilots are using computers to train for bombing missions. Then over to Lawrence Livermore Labs here in California for an update on SDI, the Strategic Defense Initiative. And finally, the real robot wars, the development of military robots at Carnegie Mellon University in Pittsburgh. Computers in the Pentagon, Part 2, coming up next on the Computer Chronicles. Computer Chronicles is made possible in part by PC to PC, the online computer migration service from PC First, moving files, applications, and preferences from your old computer to your new one. Additional support is provided by Upside Events, presenting the Digital Lifestyle Revolution Conference, where people and technology intersect.
The traditional symbols of life on a battleship are found even on the Navy's newest vessels: lines, flags, the semaphore, and the bridge, where the captain issues commands in preparation for departure. But once out on the open sea, the symbols have changed from analog to digital. The USS Valley Forge is the most advanced cruiser in the American fleet, the latest in a series of ships equipped for computer-aided electronic warfare. Deep inside its decks is the control center for a combat system called Aegis, named after the protective shield of Zeus.
Technically, Aegis is the Mark VII weapon system that's built around a spy radar, computer-controlled multifunction phased array radar that gives us the ability to track targets, detect and track targets automatically with fire control accuracy. When you combine that with a command and decision system, a computer-based system that processes information, allows you to correlate targets and keep track of the detections that the spy radar makes, and weapon control system, also computer-based, that allows you to schedule targets and create missile engagements on those targets, then you come up with an Aegis weapon system.
Aegis was developed in response to a perceived increase in Soviet sea power and to counteract the deadly efficiency of air-launched anti-ship missiles, a threat made evident by the destruction of a British destroyer during the Falkland Islands War. Aegis surrounds the Valley Forge with a protective sphere that detects, tracks, and automatically responds to any hostility up to 200 miles away. At the heart of the system is the computer-controlled Spy-1 radar, which projects beams in all directions virtually at once. Sifting through and organizing the sensor data are 3 computer systems, one for the radar, one for the weapon system, and one for the command and control.
The system is totally automated in the event that one of the 4 computers in a particular bay has something go wrong with it. The system will automatically reconfigure to cut that out and still retain the tactical guidance that we need. The way we're using the computers essentially is what's radical from other ships. For doctrine control, which is essentially an if-then statement. If a certain airplane or ship has a parameter, then it is either classified this or engaged as such.
We are up.
While the Valley Forge is not the first or the only Navy ship with electronic defenses, it marks a new degree of reliance on computer assistance. In the heavily armored Command and Control Center, sensors can identify targets as friend or foe and will track the location, direction, and speed of up to 200 separate targets. The command and decision system feeds the data to a weapons control loop, which assigns priority to the hostile targets, picks appropriate weapons, and computes trial intercepts and the time to fire. Once threats have been identified and weapons assigned, the ship's commander is faced with a major decision. Aegis can operate in manual, semi-automatic, and automatic configurations. In the special automatic mode, the system will automatically fire at targets determined to be hostile until manually overridden. The ability to carry out totally automated warfare is an option that the ship's commander regards with extreme caution.
We can, in fact, operate CIC with very few people. We typically don't, because we tend to put a man in the loop rather than leave the ones and zeros to their own devices.
The cost of an Aegis destroyer? Almost $1 billion per ship. On the other hand, the Navy estimates that even with its smaller crew, one Aegis cruiser can replace 3 or 4 conventional ships.
At the beginning of the program, Gary and I were playing a war game on a computer. Well, they use computers for war games here too, but believe me, it's not for play. This is Griffiths Air Force Base in upstate New York, home of the Rome Air Development Center. The Air Force is doing research here on the use of computers to make those life and death decisions involved in real battle management. The Air Force is developing several computer systems to improve its mission planning, battle management, and command and control functions. The two key areas that are being researched here are sophisticated networks or distributed processing and artificial intelligence or expert systems. This, for example, is called the Advanced Sensory Exploitation System. It analyzes input from different kinds of sensors, electronic, visual, and radar, to provide the commander with the best possible information on the status of the enemy. This computer system analyzes the enemy's position and makes recommendations as to flight paths that will allow for maximum effectiveness of the attack with minimum losses to the pilots. The main problem these computers are trying to tackle is one of information overload for the commanders.
The hardware we've developed, the sensors we developed, provide the military with an awful lot of information that they can't deal with in terms of how fast they can deal with it. So what we're trying to do is put some what are generally perceived as human intelligence capabilities, things like learning, problem solving, into the computer, so that the computer can do some of that data fusion, if you will, make some sense of the information that's given.
One of the keys to an effective computer system is a network of distributed processing. A network approach is particularly important in the military, where the system may have to operate in a hostile environment.
One of the main things we want for a command and control system is to be able to survive and to be able to continue to operate in the presence of hostility where you may be losing parts of the system. One of the potentials we see for distributed systems is that if I lose nodes, other nodes which remain can pick up the function that was being performed by the node that lost. Okay? What that means is I have to be able to move both the processes and the data among the various nodes, and that's what we call migration of processes, migration of data, and reconnect the users that are left to the remaining nodes themselves.
Besides networking, the other main thrust of research here is in the area of artificial intelligence, the use of knowledge-based systems to make the task of mission planning.
okay, tell me what I can hit that target with then. Rather than you going through the database and say, okay, let's see, maybe one of those aircraft is at a nearer field. You can say to the system, you schedule this for me then. You tell me what I can hit that target with, all right? And the system knows what the range of the aircraft is, what aircraft are at a particular base, what kind of armaments do you need to knock that target out, and do the armaments and the aircraft match?
That's exactly what this system does. The commander can review potential targets, have the computer match them up against resources, and check to see which targets are still unmatched. They're the ones in yellow. The commander can also support his decision-making with a laser disc-based mapping system, which provides detailed aerial views of potential target areas from maps all the way down to photos. The computer system can also be used to play war games and try out various strategies in advance. Here, the commander is creating a scenario, putting in an infantry unit, an engineering unit, and so on at a particular location of conflict. But as sophisticated as these computer systems may be, the designers say they're still just decision aids, not decision makers.
I think the important distinction is that the human is still making the decision, and that's the key. We try to provide him with as much data as we can and try to provide the assurances that the data is current and accurate, but we are not trying to build systems to take the ultimate decision-making power away from the human being.
The humans may still be important, but the computers have changed the ways of warfare. The Air Force experts here say that if the Nazis had had this kind of computer power in World War II, they would not have been fooled on the location of the Normandy invasion. And had we had computers in 1941, the attack on Pearl Harbor might never have happened. With the enemy now terrorists rather than Russians, the Strategic Defense Initiative, SDI, or now called the Ballistic Missile Defense Project, seems less relevant, unless, of course, terrorists start using nuclear missiles. Actually, the work on SDI began some 20 years ago as computer programmers took on the immense challenge of writing software that could get a bullet to hit a bullet. We're going to take you to the place where much of the SDI research is going on, Lawrence Livermore Labs here in California. The reporter is Wendy Woods.
The Strategic Defense Initiative, also called SDI or Star Wars by some, is a massive undertaking in any terms and especially ambitious in its computer-related requirements.
There are two classes of requirements that we think about. First are the functionality types of requirements, requirements associated with detecting and tracking weapons, ballistic missiles, re-entry vehicles. The functionality of forming the tracks and prioritizing targets so that target lists can be turned over to weapons so that re-entry vehicles can be attacked and destroyed before they re-enter the atmosphere. Now, those are the functionality types of issues. Then there are some non-functional or desirable attributes that we would like the system and therefore the software to exhibit. And these attributes are, we would like for the system to be able to gracefully evolve with advancing technology and with changing requirements for the system.
The key to successful deployment of SDI may depend on software with the ability to contain faults and to reconfigure the system around any failure. SDI's enormous computational demands call for exceptional hardware as well.
With the advent of multiprocessor architectures, that there's an opportunity to implement the functionality as well as the non-functional attributes of robustness and fault tolerance in multiprocessor architectures that we need to take advantage of. One of the things that we talk a lot about is trying to modularize the software and drive these modules to as low a level of simplicity as we can, and then to distribute the modules through the processor architectures.
Critics of SDI express concern that the system's software needs, perhaps 40 million lines of code, are so vast and so complex that the system could never be totally reliable.
It's very, very difficult and probably impossible to develop what we would consider to be reliable software.
And there are a number of reasons for that. The software would be enormously complex. It would be the most complex software package ever written, for one thing. And second of all, it can't be tested under realistic conditions. In order to test it, you'd have to have a nuclear war.
SDI's distributed computer system would direct a variety of new weapons, controlled from largely autonomous space platforms.
One of our key programs at the laboratory now is a ground-based free electron laser. Here you would use the large power inherent in an electron accelerator to produce visible light, and this light would be then reflected up into space, perhaps to a receiving station at a geosynchronous altitude, then back down over the area of, for instance, the missile launch to other mirrors.
Researchers describe the need for space-based hardware and software to be resilient and robust, not only to resist countermeasures like decoys, but to survive in outer space.
It will require, for the first time, to put a lot of computer processing power hardware in space. There are issues related to that. We've never put big software systems in space either, and the taxing nature of space on not only the processor but also on volatile memories provides us some questions.
Both decoys and anti-satellite weapons represent possible Soviet responses to a defense. One warhead may be accompanied with hundreds or more light decoys, which would look to inexpensive sensor systems pretty much like the real thing. There may be 40,000 warheads. That times 100 gives 4 million objects. Processing 4 million objects in typically 1,000 seconds is a very stressing kind of requirement.
It's somewhat discomforting to think that a future war could be in the hands of two opposing computers. But when you think about it, war has always been a battle of technology.
Absolutely, it has always been like that for centuries. If you had guns and I didn't have guns, I'm done for. If you had cannons and I didn't, there was no way I could fight with you. It goes back as far back as you want. And if I had sophisticated missiles and you didn't have them, as in the Middle East War, in '73 or whenever, there's no competition. And so nobody is going to be foolish enough to say, if you have a weapon that is of demonstrated superiority, then I'm going to come and sacrifice lives. So if a robot fights a robot, and one of them has a clear superiority, then people will say, that's a winner.
One of the concerns about sophisticated computers in the military is the delegation of decision-making to computers. And indeed, it is possible that in the short time frames of ballistic missiles, a computer might have to make its own decision to take defensive action.
A massive launch that corresponds to all of the images of an attack could be dealt with certain precautions associated with multiple phenomenology, measuring the nature of the threat and so forth, and allowing the system to engage the threat, seems to be the kind of philosophy that we would probably adopt, especially in a situation where the system itself was under attack. If a direct ascent ASAT was launched against the system, it would be likely that the system would be allowed to protect itself.
While it is scary to think about the use of computer technology for war, Professor Reddy thinks computers may in fact prevent wars, in the same way that many argue nuclear weapons have prevented major wars.
War is bad for people anyway, and so why not have robots fight robots and get people out of wars, and those people that have better robots will be declared winner. Some such scenario could in fact happen in the 21st century, because once one has a superior technology, which is clearly demonstratable, then everybody realizes that there's no way one can in fact overcome that advantage, and automatically people will in fact back down from wars.
While the debate goes on about high-tech warfare and computerized defense systems in space, Lieutenant Colonel Audley says the debate over sophisticated computers in the military is really no different than the debate 70 years ago over airplanes in the military.
When airplanes came about, we didn't know exactly how they were going to fit into the military arena, and we started using them as observation platforms, and then we found that we could shoot at one another from them and drop bombs from them, and they radically changed the nature of warfare. They made battleships virtually obsolete. SDI is another arena where we see incredible advances in technology, and in this case perhaps being directed to make another weapons system obsolete, in this case the ICBM.
Much of the defense-oriented computer research in this country is funded by DARPA, the Defense Advanced Research Projects Agency. Some critics say that puts an inappropriate military bent on basic research, but Professor Reddy doesn't share that criticism of DARPA.
They were responsible, for example, for the invention of time sharing. They were responsible for the invention of support of artificial intelligence research for a long time. Much of the robotics research. They were responsible for the computer networking research, the ARPANET, which is now permitting all kinds of communications and electronic mail. So many breakthroughs that came in this field over the last 30 years have come from universities through support, unrestricted, unclassified research support from DARPA.
There are indeed many civilian spin-offs of technologies developed for the military. For example, the research going on here at Carnegie Mellon University may lead to robot tanks, but it may also lead to safer cars.
The military environment is a microcosm of our general industrial environment and general environment. For example, the technology that we're looking at, we are hoping will be primarily used in civilian sector for cars that will drive themselves, so that if I'm drunk or fall asleep at the car or not paying attention, I would not be into a fatal accident. And currently the single largest source of deaths in this country, more than 500,000 a year, is because of automobile accidents. We believe this technology can in fact eliminate 90% of those kinds of deaths.
The consensus of opinion seems to be that whether our computer research ends up in military or civilian applications, there is little doubt about the importance of the task at hand.
The most important technologies for the future are very clear. Computers, communications, artificial intelligence, robotics, materials technologies that will help in all of these things. And semiconductor technologies, which are electronics, which are integral to all of these things. Fiber optics, again, for communications. Satellite technologies. Essentially all the ones where we currently have significant superiority over all other nations. And it's a question of whether how long we will maintain the superiority.
That's it for our special two-part series on computers and the Pentagon. If you have any questions about anything you saw in the series, please check out our website at computerchronicles.org. Thanks so much for joining us, and I hope we'll see you here again next week on the Computer Chronicles. Computer Chronicles is made possible in part by PC to PC, the online computer migration service from PC First, moving files, applications, and preferences from your old computer to your new one. Additional support is provided by Upside Events, presenting the Digital Lifestyle Revolution Conference, where people and technology intersect.
To purchase a videotape copy of today's program, call toll-free 1-888-310-7850. Please specify the show number and the topic.